All right, here we have, this is review 3. So I've done 3 reviews, I've done 2 reviews already. Solvation process, I talked a little bit about colloids, solute solvent, polar solvents, nonpolar solvents, etc. Now, one of the ideas is that I also did why water is polar. And we have to go back to chapter 8 for that. For instance, I did carbon tetrachloride. I went back to chapter 8 and I did the molecular geometry of carbon tetrachloride, of chloroform, which is a polar solvent. I did water, and I'm going to do a few others. Okay? Another fairly common solvent, obviously not as common as water, but a common one, is called carbon disulfide. Carbon disulfide. Now, many of you may be able to tell me what the geometry is of carbon disulfide right away. Yes?
Kind of looks like Mickey Mouse.
Kind of looks like Mickey Mouse. That's water. Mickey Mouse is kind of like water, sort of. No, it's not like Mickey Mouse. I don't think, if I get your meaning. So let's do the molecular geometry of carbon disulfide. Okay? In organic chemistry, we use carbon disulfide, and it is extremely stinky. It is overpoweringly yuck. Okay? So let's look at the geometry of carbon disulfide. Okay? You ready? Okay, so carbon. Okay.
That can be polar, though.
Excuse me?
Can that be polar?
Well, that's what we're going to find out. Let's do the geometry before we make any comments. Okay, let's do the geometry. Do it first and then see what happens, okay? Okay. Well, carbon's going to have to be in the middle. Usually the one with the greater number of bonds to it is going to be in the middle. It's a pretty good generalized thing to say. So you write down the valences. What's the valence of sulfur? No? No one? Periodic table might help you. How many electrons does sulfur have in the valence state? Carbon, how many electrons in the valence state? What's the valence of sulfur? Does anybody know how to find their periodic table in their chemistry book? This is after lunch. People are digesting. No? What is it? No. No, the valence, the number of valence electrons. The valence state is the number of valence electrons available. 6 for sulfur. Okay? And what about carbon? 4. Okay, so that's going to be 16. Minus 2 each. So that's minus 4 is going to be what? 12. Okay. Now what you want to do is you want to complete the valence. What do I mean by complete the valence? What does that mean?
I'm going to fill up
the outer shells, right? The outer. So this has 2, it needs 6 more. So that's 12, right? So this is going to be bonds, right? This is going to be 2 bonds. And this is going to be complete valence. So, but how many electrons? Carbon is a nonmetal. And nonmetals, as a central atom, must have at least 8 electrons. Can they have more than 8?
Yeah.
Yeah, absolutely. Yeah, absolutely. Okay? So what? So what? So what do we do? We have to take 2 from here, and you put them here. And we take 2 from here, and put them, exactly. We're going to have 2 double bonds. So you're going to look like this. Right? Kind of like, if you'll recall, kind of like carbon dioxide. Is there a similarity between the valence of oxygen and the valence of sulfur? Are they similar or are they the same?
The same.
They're the same. 6, right? And you may remember with our work with gases that carbon dioxide is a linear molecule. There's no excess electrons on the central atom, so it's going to be linear. So what has a greater electronegativity? Sulfur or carbon?
Sulfur.
Look it up. Chapter 5, look up electronegativity. Chapter 5, I think, right?
Yeah.
Sort of towards the end of 5.
Sulfur.
They're kind of like, instead of looking at the table of contents, they're,
Here.
she's got, is that electronegativity?
Maybe it's not 5.
Maybe. I was thinking it was about 5. You got it? Anybody got it?
Yeah.
What do you got?
So you're looking for sulfur and
Carbon.
Carbon.
What's sulfur?
It's on page 181. Well, carbon is 2.5.
2.5. The electronegativity. And what's sulfur? Should be in the same table, right?
Yeah, it's the same.
It's the same? Similar?
Yes. No,
Somebody
it's
want-
the same. They're the same.
They're the
2.5.
same, so they're approximately the same.
Yeah,
You want to look up maybe on the web, they're going to be different.
probably like.
So why don't you look up on the web carbon and sulfur, and we'll come back to that. Is that okay while you look that up? So anyway, the point is this. The same or not the same. If there's any dipole there, they're going to do what? You want to look that up there, Abby? Okay. Don't look at me. Don't listen to me. You have my permission to completely ignore me.
Okay.
So even if there is or isn't a dipole, are they going to cancel each other out? Yes or no? Are they going to cancel out the dipoles? Are they going to cancel out the dipoles? No? How many people have been here before? How many people have never been in my class before? How many people aren't here now? Is there anybody out there? I'm asking you a question. Let's look at oxygen. Oxygen is clear cut. Oxygen, which is a stronger electronegative element? Carbon or oxygen?
I got for the web, the electronegativity of carbon is 2.55, and the electronegativity of sulfur is 2.58.
All right, 2.55 and 2.58.
Yes.
So sulfur is bigger, correct? Not by much, right? But it's certainly bigger, yes?
Yes.
So the dipole's going that way, correct?
Yeah.
So they're going like this, and they're equal, right?
Yeah.
They're pulling. Will they cancel?
Yes.
Yes, they will cancel. What question did you think I was asking 2 minutes ago when I got no response?
Same question that you just asked.
Ishmael, you're actually responding. I like that. What did you just say?
The same question that you actually asked just now. The same question that you asked.
But you had a moment to think about it.
I don't want to think about it, but I still had the same answer. I kind of nodded, but I didn't voice my answer.
You didn't voice your answer. Okay, excellent. There's an old country western song in the United States goes, "You can't be a beacon if your light don't shine." Okay? You understand? That's an old country western song from the United States. You can't be a beacon if your light don't shine. Okay? Understood? Now, so shine that light, Ishmael. Shine it bright. Okay? You understand? All right. So, you need to know chapter 8. in order to do chapter 15, because not every solvent is going to be water, not every solvent is going to be polar, not every solvent is going to be nonpolar. You've got to be able to see, well, if I have carbon tetrachloride, is that going to dissolve methane? Or is it going to dissolve sodium chloride? Yes? Does nonpolar dissolve sodium chloride? Does nonpolar solvent dissolve sodium chloride? Yes or no? And remember, you can't be a beacon if your light don't shine.
Repeat the question, please.
Does carbon tetrachloride, can that dissolve sodium chloride? No, that's not what I asked you, is it? What did I say? Can a nonpolar solvent dissolve sodium chloride? These questions are taking so long to answer, I forget what the original question was. You don't know? Are you going to tell me that we've been doing this for 2 or 3 weeks and you still don't know that like dissolves like, that nonpolar dissolves nonpolar, that polar dissolves polar? You don't know that? What are you going to do tomorrow? I'm chastising this entire class in front of the world. Shall we mention names and addresses? Shall we? So these people can come and find you?
A nonpolar solute cannot dissolve in a polar solvent.
A nonpolar solute cannot dissolve in a polar solvent. Excellent. I like that. Give me another truism.
A polar solute cannot
A polar solute.
cannot dissolve in a nonpolar solvent.
Isn't that what you just said?
No, I just switched it.
You just switched it. Okay. But polar dissolves in polar and nonpolar dissolves in nonpolar, correct? And nonpolar dissolves nonpolar and polar dissolves polar, correct?
That's what you said.
Is carbon tetrachloride polar or nonpolar? Is carbon tetrachloride polar or nonpolar? It is absolutely, positively, utterly, top down, left, right, in, out, anywhere a squirrel can go, non-polar, not polar. And how would you know that? By guessing, Mustafa? No. By actually working out the molecular geometry.
I was thinking the carbon would be in the middle.
It is in the middle.
Oh wait, never mind. Yeah, that makes sense because it could be like the carbon next to the.
I know, the chlorine kind of throws you off, because when you think of chlorine, you think of like polar, right? I know, absolutely. But by May of your first year of chemistry, you should recognize, what should you know right now? What should you know by looking at carbon tetrachloride? What should you be able to do right off the bat without much thinking? Amanda. She's from South Africa, but she's one of my best students.
We have to know.
I'm sure there are millions of Amandas in South Africa. I didn't really identify her. She's actually very beautiful with long hair. Okay, she's giving me the horrible look. If looks could stop, if looks could direct traffic. Okay, what was my question?
What you should know when you look at carbon tetrachloride.
Yeah, carbon has 4 bonds, right?
Yes.
Yeah, carbon always forms 4 bonds, and there's 4 chlorines. So there's not going to be any extra electrons on the central atom, so it's going to have a regular geometry. 4 bonds to me, shouts of, I hear it, wait, hold it, what's that sound? Carbon tetrachloride. What's that sound? Tetrahedral. That's it.
And so they cancel each other out.
Yeah, they cancel each other out. Okay? They're all going this way. Right? Why? Because I I have 4 bonds, correct? I think I did this on review part 2, right? But I'm doing it for you because you're a different class. Okay. Shall I do it quickly? Is that okay? Ahmed, are you okay with that? Okay, Ahmed's one of my best students. When I think of Ahmed, I simply think of the word visually of chemistry. It's unbelievable. He's unbelievable. Okay, so. So I'm going to have 4, 28, 32. 7, 7, 7, 7 plus 4 is 32, correct? Mm-hmm. Minus 8 is going to be 24. Complete the valences. 6, 6, 6, 6, minus 24, 0. Yes? Carbon tetrachloride, CCl4, correct? Are you all right with that? Okay. Regular geometry, they all cancel. As opposed to CHCl3, chloroform. I think this is where I ended. I ended my part 2 with this, right? These will cancel. Right? This won't cancel, will it?
No.
This will cancel, but this won't. Therefore, it's polar. Right? But is it extraordinarily shut the front door polar? Is it? No. No. It's polar, but it's not like crazy polar. Yes? What about ammonia? Is that going to dissolve in water? Ammonia, NH3. Try that one on for size. Try ammonia on for size.
Yeah, it does.
It does? It what? It's soluble in water?
Yeah.
Is that what you said? And are you guessing? Which is fine. Guessing is good. I like guessing.
Because there's ammonia in bleach, right?
Ammonia essentially is not in bleach. If you put ammonia in bleach, run.
Yeah.
It is highly soluble.
You put, that means you make chlorine gas. Never mix bleach and ammonia. You produce tons of chlorine gas.
It is soluble.
Run. Bah.
It is soluble. Because it's electronegative. Very
Well-
Well, you just said words. House. You just said words. Ammonia is soluble why?
In water, because it's electronegative.
No. No. Something is not soluble because of its electronegative. Something is soluble because of the geometric structure. All bonds, unless you have nitrogen on both sides, that kind of bond, or oxygen on both sides, right? Diatomic, they're the same. All bonds are polar unless you have the same element on either side of the bond, right? So differences in electronegativity, look at carbon tetrachloride. Carbon tetrachloride is nonpolar, and there are differences in electronegativity, but let's do the geometry. Why are you balking at this? Why are you balking at this?
What's walking?
Looking.
What's balking? Oh my God, is that like an American thing?
No.
Balk,
When you stare at something, you're
balk. Does balking have a meaning to non-Americans?
Yes.
No?
That must be a New Jersey word.
Gawking doesn't have
No, it's Missouri. Can you pronounce St. Louis? The St. Louis Cardinals Missouri has a baseball team. Balking. To balk. You know what? Does anybody know what baseball is?
Yes.
When a balk is when you essentially, I'll give you the short version, when you pretend to throw it to first base but you really don't, or you pretend to throw it home but you really don't. You can't do that. You can't go. You Can't do that. There's rules, a lot of rules, but a balk means something the pitcher does. Whatever, it's a long story. But anyway, balk, I guess it's a baseball term. But how many people are hesitating with doing the actual geometry? Why are you hesitating? Matthew, you never came to school until February. I mean no disrespect. Well, maybe I do, but I'm kidding. But you want to try that? Why don't you try that on for size, Matt? All right. So NH3 is ammonia, right?
Yes.
Okay. All right. So I write a C on the board. Okay.
Good job.
Abby, you're enjoying my mistakes far too much. Okay. NH3. All right. So what would the structure be for that? NH3.
On the middle.
N in the middle, and then 3 H's. Matt, are you directing these? Are these your minions that you're directing them to say this? That's really very well done. He's doing this telepathically. I like that. He's manipulating Pranita and Abby to say that. I like the way you're doing that. You're controlling people around you. That's amazing how you did that. Okay, so I write a C again. Okay. I got carbon on the brain. Okay. So it's going to be like this, right? All right, correct? Now, so then you do the valence, right? What do I do?
It's supposed to be H.
H last.
Okay. All right. What are you laughing at? Okay. Ahmed likes this. He's enjoying me making complete mistakes. All right, so NH3, right? Yeah, do the valence now. What's the valence of hydrogen? Matt? Oh my God, I just saw a 1. Excellent. It's amazing how he's doing that. 1, 1, 1, 5, right?
Yeah.
8 minus 6 is 2. Where did I get minus 6 from? Where did I get minus? What did I do? I did minus 6. What does that mean?
They unbonded electrons.
No.
No, the bonds are on
The bond. I have 3 bonds. I hooked up 3 bonds right away. So I have to get, I only have so many valence electrons I'm working with. The total valence, 8, means the total electrons I have available in the bonding process, correct? That includes everything. That includes completed valences, bonds, everything. Excess electrons, everything, right? You all right with that? Okay. So I got 2 left. I've got to put them here for 2 reasons. I have nowhere else to put them. I can't put them on the hydrogens because they're already complete. 2's it, right? Because they want to be like helium. We don't use the O word, right? Excellent. O word, octet. We don't use that. Octet is for aliens who are not as bright as humans. Yeah, we don't use like rules of thumb. We don't like those, okay? So, right. So how many electrons must the central atom have if it's a non-metal? I'll give you a hint. After lunch. 8.
Oh, 8.
Oh, okay. All right. Yusuf's like, oh, I should have gotten that one. Okay, fine. Okay. So you have to put an 8 one there, right? How many can you have around a metal?
8.
No.
6, 0, 4.
You can have 4 beryllium hydride, Be.
Less than 8?
Yeah, you can have less than 8. Yeah, you can have less than 8. 6 aluminum chloride, 6, right? Right. Okay. So metals, we're cool with metals. So what does that pair do? Well, that pair, I just so happens I have. See this, right? Well, if I didn't have that central pair, I would have this. Can you see this? Does that come off on this machine? Yeah. I'd have this. I'd have 3 equal bonds in the same plane, right? Mm-hmm. Right? Wouldn't I?
Yes.
Okay. But because I put this excess pair here, that's forcing these out of the plane. Not tremendously, just enough to annoy everybody. Okay? Just enough. I'm kind of forcing them out. Not bad, right? Not as much as if it were a tetrahedron, but not too much, right? So then what I'm creating here is this excess pair there. So ammonia, is it polar or nonpolar?
It's polar.
It's polar. So will it dissolve in water?
Yes.
Matter of fact, it is one of the more, or if not the most common, ammonia is common. It is one of the most common gases that is the most soluble. It's one of the most soluble of the common gases. Very soluble. Very soluble. Yes? Clear? Yeah? Are we all right? All right, now. So I think we've kind of exhausted how to determine the polarity of gases, how to determine the polarity of solutes, how to determine the polarity of what? Of solvents. Polar dissolves in polar, nonpolar dissolves in nonpolar. How does something stabilize an emulsion? Right, we did that. We talked about that. So you're going to have to look at the other review things. Okay, let's see. Throw me some terms out here, and I'll tell you whether or not we're kind of approaching an end here. I want to finish this in the next 5 minutes. Let me get that. I have the actual test right there. Let me get the test, and what we'll do is maybe we'll look at that a little bit. Okay, is that okay? All right. Anybody have any words that they want me to explain? This is your test. Mustafa, are you participating? You're strangely quiet. Are you quiet because of you're up to an alternate activity of some sort there? You're okay? Everything's good? Cool? Excellent. Yes, Fabiana. Deliquescent. What is... Somebody tell me what that means. What is deliquescent? That's actually a very nice pronunciation of that word. It's actually pronounced deliquescent. Matt, what does deliquescent mean?
A substance that removes enough water from the air and forms into a solution.
Is that what it says? Let's see. Let's check Matt's facts. I am very impressed. Matt, how did you do that?
I opened the book and...
But what's that in front of you?
This is my textbook, my copy book.
Notes.
Notes.
Wow. Enzo, are you slightly overwhelmed?
Sort of. A bit.
Yeah, you had that look about you, like, what the hell? What is he doing? I mean, that's like amazing. Yeah, deliquescent. So, anybody else want to verify what deliquescent is?
Tending to absorb moisture from the air and dissolving it.
Yeah, tending to absorb moisture from the air. Okay. Is that what it says?
No.
What does it say? Deliquescent.
Yeah. It removes water from the air.
It removes water from the air. To the point where it starts to dissolve in itself, right? Is that what it says?
Yeah.
Yeah. Like, what's something that's very deliquescent? I talked about it in class. Zinc chloride. When I used to have my students do, they would add zinc to zinc chloride, zinc to hydrochloric acid, right? When we did constant ratios, this is what they would do. We did it as a stoichiometry lab. So let's do a stoichiometry lab so that you can say we did at least one lab this year. Okay? So I'm going to give you zinc plus all the hydrochloric acid you'll need. Matter of fact, I'm going to give you tons of it. Okay? I'm going to give you plenty of it. Okay? So then what I'm going to do is, you have so much hydrochloric acid, you're going to say, well, how do I know when that's all gone? Well, you know what I'll do? I'll say, you know what I'll do? I'll give you tons of zinc instead. I'll give you tons of zinc. So you take a beaker and you put it in, let's say 6 molar HCl, right? Very concentrated. It's about half concentrate, right? Concentrated HCl is 12 molar. then you put in zinc. Put in zinc, and you have all these plates of zinc in here, right? And then it gives off hydrogen gas, right? Right? Gives off plenty of hydrogen gas. Yeah? Yes? And then you come in the next day, and there's no hydrogen gas being given off, and there's some zinc underneath there. There's some zinc there. Okay? So then what you do is, you find out how much zinc you put in. You know that because you kept track of how much zinc you put in. Yes? And then you measure the amount of zinc left over. And can you determine how much zinc? Can you determine how much zinc was used?
Yeah.
Yeah, of course. Right? Yes? You can do that, right? Okay, good. Because I can find the mass of what was left over. Then what I do is I pour this stuff out, and I find out how much, I evaporate off the water, and can I tell how much zinc chloride was produced? Sure. I pour it into an evaporating dish, I put it over a flame, and I get these crystals here. Right? I get these crystals, and then I find the mass of this, correct? And then I know the mass of the empty evaporating dish. I know the mass of the evaporating dish with the crystals in it. So now I go to my equation and I say, okay, that's fine. Now, what's the mass of zinc? Anybody know? Periodic table?
65.
65. Is that okay? We'll say 65. And what's the mass of zinc chloride? 65 plus 70 is 1.
No, 65 plus 35.
No, zinc chloride.
135.
ZnCl2.
Oh, yeah.
You need a calculator? 135. So what is 65 over 135? You need a calculator?
Sure, what about the stuff that's going to do?
I'm an old person. Are you, what are you saying to me? What about the stuff that's on the test? You're assuming that what I'm putting on the board isn't?
Yes.
Oh. Isn't he brash, don't you think? I'm teaching. 0.48, right? Well, what happens if I said, well, I used, let's see, I used 5 grams of zinc. I used 5 grams of zinc, all right, and I got back, let's see, I found the mass of the zinc chloride, and I got 8 grams of zinc chloride. What's 5 divided by 8?
0.625.
0.625. So instead of getting 0.48, I got 0.625, right? If I put in 5, how much should I have gotten? If I used 5 grams of zinc, how much zinc chloride should I have gotten? You don't remember your stoichiometry? What's the question mark? 5 times 135 divided by 65 is what? Nine point something.
10.3.
I'm sorry, 10 point something. What is it? 10.3?
8.
10.38?
10.38.
That's what I should have gotten. Correct? Now, the problem with that lab is this. This is the problem with the lab. A lot of mistakes with the lab. Problem with the lab is that zinc chloride is very deliquescent. You see that? So as I'm trying to heat the water off, and then I take it from, You gotta let it cool, and then you take it to the mass, the Valence. It's absorbing water. Very deliquescent, zinc chloride. An excellent lab to do, because it has air all through it, and the point of a chemistry lab is oftentimes to be able to determine where error came from. Systematic error, and part of the error comes from the fact that you're actually using zinc chloride. Zinc chloride is very deliquescent. So what would zinc chloride do to your measurements? Would you get high measurements or low measurements? No, you would get high measurements. Instead of getting 10.38, you'd get what? You'd get values greater than 10.38. The only reason you might get something less than 10.38 is if you kept doing it so much that you simply decomposed the zinc chloride. That sometimes happens. Yes? You get it? Who's taking IB chemistry next year? Yeah, you'll do that a lot next year, hopefully. But you'll be your only weak point will be with some of the lab work, but you're going to be, in terms of theory, you're going to be doing, I think you'll be very well prepared in terms of theory. Okay? Yes? All right. So, what else? Anything else? Shall I look at the test briefly? Okay. All right. So, predict whether or not something's soluble or insoluble. I'll give you the 5 things. I'll give you a bunch of things just right on this page with a bunch: sodium bromide, barium sulfate, calcium sulfate, ammonia, methane, zinc sulfide, sodium bromide. So you have to be able to determine, I'm giving you molecular structures here, and you have to be able to go back to chapter 8 and say, well, wait a second. Is that a polar substance or a nonpolar substance? Let me see if I can figure that out. So I'm not just wasting your time. What are some of remember there's a table in chapter 15 on common hydrates? Remember? What are some common hydrates? Yes?
Magnesium sulfate.
What's magnesium sulfate called? It's called Epsom salt. Right. What's another very common hydrate? Borax. Borax.
And
barium sulfate? I don't think.
Barium hydroxide.
Barium hydroxide is a common one. Is barium sulfate soluble?
I don't. Barium sulfate.
How about calcium phosphate? Is that soluble? You guys learn anything in biology?
No.
Calcium phosphate is bone. You better hope that bone is not soluble. How about calcium carbonate? Is that soluble or insoluble? Mustafa?
That's fish bone, not fish bone.
It's insect, exoskeleton.
That's exoskeleton of like mollusks. A lot of mollusks, like clams, oysters, arthropods, crabs, right? Lobsters. So you better hope that they're not soluble. Yes? Yes? So that's pretty good. Let's see. Emulsions. Is paint a colloid? Yes, you bet your bottom dollar. What's a hydrate?
Hydrate is something that takes water, absorbs water.
No, is a hydrate something that absorbs water, or something that is hygroscopic, something that absorbs water?
Something that's hygroscopic.
Something that's hygroscopic. When is something so hygroscopic it makes its own water solution? What's that called? We just said it. Sounds very French. Deliquent. What did we say it was? Deliquescence. Right? What's efflorescence? What's that? Efflorescence. Yes.
Okay. Oh,
Yes, Matt, the Hungarian. The crazy Hungarian Magyar. I love it.
When you lose moisture and turn to powder, when you're exposed to air.
Not necessarily powder. It's just when a hydrate loses its water.
A hydrate loses its water. And what's that called?
Efflorescence.
Efflorescence. Efflorescence. I was mispronouncing it, wasn't I?
Yeah.
Efflorescence, yeah.
I think it's F1.
What was that noise?